Hi, we're looking at 6.2, confidence intervals and hypothesis testing for the difference in proportion. So we had looked at those things for a single proportion, and now we're going to look at the difference in proportions. So that means we are going to have one proportion, we'll call it, say, P1, and then we'll subtract another proportion. And we'll test if there is basically a difference between those two proportions, or we'll find the estimate of the difference between those two proportions. So just a reminder, it is a confidence interval that we use to estimate the difference in proportions. And a hypothesis test answers a specific question, such as, is there a difference between two population proportions? So the difference in proportions, like I said, is the P1 minus P2. So instead of just using a single P for a population proportion, the new parameter really is the difference of those two proportions. So we're going to look at an example. Two types of medication for hives are being tested to determine if there's a difference in the proportion of adult patient reactions. From a random sample of 40 adults, half were randomly assigned to take medication A, and the other half were assigned to take medication B. Of those given medication A, 20 still had hives after 30 minutes, and 12 of those given medication B still had hives 30 minutes after taking medication. So if we summarize some of the information, we can say that the sample for medication A, or N sub A, is half of 400, so that's 200. And then the sample size for medication B is also 200. And then we want to find the sample proportion that still have hives using medication A, and after 30 minutes. And so it's telling us it's 20 out of the 200, which gives us a sample proportion of 0.1. And for medication B, there were 12 out of 200, which is a sample proportion of 0.06. So let's start off by wanting to find a estimate, so a confidence interval for the difference between the proportion of patients that had hives after 30 minutes for medication A and medication B. We're going to use the same 4 steps that we did for single proportion. So we're going to want to identify the sample sizes. So in general, N1, N2, and then the sample proportions, P hat 1, P hat 2. And then determine which confidence interval we want to use. And then just like before, we're going to use 90%, 95%, and 99%. The second step is to check to make sure that the conditions hold, that we can apply the normal distribution. And so we are wanting to ensure that our sample statistic, which is the difference in the sample proportions, is nearly normal. To do that, we want to ensure that the data are independent, both within each sample and between each sample. So we now have a situation where we have 2 separate samples, one for each of the 2 things that we're comparing. So we want independence within each sample and between each sample. And that is generally satisfied if we have random sampling. Or if it's an experiment, we want a randomized experiment. We also have a success-failure condition. We are going to use the sample sizes and the sample proportion from both samples. So we want N1 P hat 1, that to be greater than 10. So that would be the success, the number of successes for the first sample, and then the number of failures would be n1 times p hat 1, also greater than 10. And then for the second sample, we're just going to repeat that. The third step is to calculate. We need the standard error. We will use the sample proportions to calculate the standard error, and then also determine what the z-value is for the given confidence level. So the standard error for the difference in proportion, we're going to have a big square root, just like we did for a single proportion, and it's going to look real similar. We're going to take sample proportion 1 times 1 minus sample proportion 1 all over the sample size 1 plus p hat 2 times 1 minus p hat 2 all over n2. And then to get the confidence interval, we take the sample statistic, so p hat 1 minus p hat 2, the difference in the sample proportions. We're going to add and subtract the z-value times the standard error. So it follows the same pattern as for single proportion, where we take the sample statistic, add and subtract the z-value times the standard error. The fourth step is to conclude, and that is to interpret the confidence interval in the context of the problem. So let's practice with the example and construct a 95% confidence interval. We have already identified the sample sizes and the sample proportion, so let's check the conditions. We're going to take n1 times p hat 1, so that's the 200 times 0.1. That gives us 20 successes. That's greater than or equal to 10. And we'll check the first sample's failures, so n1 times 1 minus p hat 1, so 200 times 0.9, and that's 180, also greater than 10. And checking for sample 2, n2 times p hat 2, we have 200 times 0.06, which is 12. And then checking for the failures from sample 2, 200 times 1 minus p hat, so 0.94, which will be 188. All right, so those are both greater than 10, greater than or equal to 10. So we can assume that our sample statistic is approximately normal. So third step, here's where we're going to calculate some things. So let's calculate the standard error. We have our big square root, and we take, first off, p hat 1, so 0.1, times 1 minus that, so 0.9, divided by the sample size of 200. Add to that sample proportion 2, 0.06, times 1 minus that, 0.94, over a sample size of 200. So the calculator will give us the result of 0.027. And our z-value is 1.96 because we're using a 95% confidence interval. So we can construct the confidence interval. We'll take p hat 1 minus p hat 2 plus or minus that z star value times the standard error. So p hat 1 minus p hat 2 is 0.1 minus 0.06. So that's equal to 0.04. So 0.04 plus and minus our z-value, 1.96, times the standard error, 0.027. And that results in a lower bound of negative 0.013 and an upper bound of 0.093. Or in percentage, we have a negative 1.3% to a positive 9.3% for the confidence interval. Step 4, we would interpret the confidence interval to mean we are 95% confident that the difference in proportion of patients with hives after 30 minutes for the two medications is between negative 1.3% and positive 9.3%. So the lower bound is a negative number. That means the confidence interval includes the possibility that the medication A has a proportion that is lower than the proportion for medication B. And the upper bound goes all the way up to 9.3, so it is a possibility that the medication A is up to 9.3% higher proportion than for medication B.